Today I will be talking about LEX, a language extraction NLP engine prototyped to identify language of interest. My name is Knarig Arabshian, and I am a Senior Knowledge Engineer in the Federal Reserve Bank of New York's Technology Innovation Team. Before I begin, I'd like to preface this talk by saying that the views that I express are my own and do not necessarily represent those of the Federal Reserve Bank of New York or the Federal Reserve System. LEX is a language extraction tool that identifies language of interest. Its primary use case has been to identify risk language within supervision's risk reports. However, it can actually be applied to many other use cases. LEX is the first custom-built NLP software put into production in FRBNY and has since been rolled out to 800 users within New York Supervision and across other FRS banks. Before we dive into the details of LEX, I'd like to begin by introducing the topic of natural language processing. NLP is a subfield of artificial intelligence and computational linguistics, and is concerned with the understanding and generation of human languages. Although NLP has gained quite a bit of popularity in the past few years, it is not a new technology. Computer scientists have been working on NLP problems since the 1950s. However, many AI algorithms require enormous amounts of computational power to produce accurate results. Since the advent of cloud technology, it has become possible to process these algorithms accurately, and hence NLP and machine learning have become more and more prevalent in industry. Although NLP is considered an AI technology, in the computer science world we refer to AI as augmented intelligence, as it aids humans in processing and synthesizing extremely large data sets, but it cannot replace them. In order to appreciate the difficulty of understanding language automatically, let us look at current-day technologies that use NLP. We are all familiar with everyday technologies such as search engines, personal assistants, and social media. However, what goes on behind the scenes of these technologies can be quite different. NLP tries to resolve the tension between syntax and semantics. Syntax is the structure of a sentence, whereas semantics is the meaning behind a sentence or phrase. Let's take a look at the phrase text mom. A personal assistant will process this phrase as a command to invoke the text messaging application and create a text message to the contact labeled mom. However, a search engine will process this identical phrase very differently. It will look for websites that contain the phrase text mom or other phrases similar to it. So although both applications are processing a syntactically identical phrase, the outcomes are very different because context matters. How does this affect how we solve NLP problems in the bank? It affects us very much. We are using NLP to identify language of interest from risk-related reports. These reports often have language which is nuanced and contextual, as well as repetitive. Hence, the ideal solution would be to use both rule-based and machine learning techniques to identify contextual language and its patterns. We have done this by using a lexicon of risk-related language built by supervision subject matter experts, as well as pre-built open-source machine-learned word vector models. The LEX engine sits inside of a comprehensive architecture. It is composed of three main components: a preprocessor, the engine itself, and a postprocessor. The preprocessor takes in documents of different types, such as PDF, Word, or Excel. These documents are processed in batches and are converted to annotated text for the NLP engine to ingest. The NLP engine takes the document as well as a lexicon of terminology and a pre-built word vector model. It processes the document sentence by sentence, and using a unique algorithm, it identifies risk sentences and sends these along with other statistical data to the postprocessor. The post-processor is the component that stores these sentences and also generates different ways a user can interact with the output. It can highlight the sentences in the original documents for the user to peruse. It can also generate different graphical user interfaces for the user. LEX has a flexible architecture such that use cases can be broken down by various lexicon types, such as BSA AML risk or climate change. LEX also outputs sentences in an annotated format called JSON, so that end users can perform further analytics on these sentences and build their own dashboards. Let's look at what supervision analysts did before the LEX engine came into existence. I will go through an example of risk identification. Information provided by the firms is used for a variety of supervisory work products. To prepare for exams, examiners will review documents for the understanding of the firm's businesses, product lines, performances, and risk issues, and to determine the focus of the exam. For continuous monitoring of a firm using their MIS to keep abreast of the firm's activities and risk profile and prioritize coverage, this information is used as a basis for assessments to management and for discussions with the firm. Information is also used for risk identification, where examiners try to connect the dots across firms or across risk. Through a review of the documentation, they identify trends, outliers, and concentrations. These activities were done manually by reading, highlighting, and summarizing the documents. You can imagine how difficult this task is when supervision receives a massive number of reports from the firms it monitors, and all in different formats. Reports that are provided by the firms have grown exponentially. Given the volume and variety of the content, supervisors are unable to analyze all the data, and hence they are not able to connect the dots between cross-firms or cross-risk information. To illustrate this, let us look at how tedious this process was. I will go through an example of a public document and show you what supervisors used to do. Examiners go to team sites, usually in SharePoint, to access a large set of documents. They would have to figure out which files to choose to read, either by perusing a number of documents or paying attention to the document names and types. After choosing a file, examiners read through the file to identify risk language. As can be seen in this example document, these files are unstructured and have a variety of different formats within it, such as text, charts, and graphs. Scrolling down, a sentence catches the analyst's eye as a risk-related sentence, and she highlights it manually. This particular sentence catches her eye because it is talking about banks with significant exposure. Now let us see what a day in the life of an examiner looks like using LEX. LEX processes all the documents in the SharePoint team sites in large batches. It creates a table of contents of all the sentences identified, so the examiner can quickly glean the results. By clicking on one of the sentences, she can go directly to that part of the document where the sentence is highlighted and continue reading it in context. LEX highlighted the particular sentence the analyst had highlighted manually, as well as other sentences. It also shows the users why the particular sentence was highlighted, because it found the terms significant and exposure, which is exactly why the analyst would have highlighted the sentence manually. Aside from the PDF highlighting, LEX gives the flexibility of generating different user interfaces on various BI tools. This one was built by a colleague in supervision using Tableau and showing different frequently matched rules as word clouds. LEX was built with scalability in mind. It scales in terms of use cases, security, and processing power. LEX allows versatile applications to multiple portfolios. Each portfolio can have a number of process flows or use cases. Use cases are determined by customized lexicons. For example, use cases in the portfolio that contains climate risk or BSA AML risk will have their own lexicons. For each of these use cases, subject matter experts will create a lexicon, and LEX will identify the sentences pertaining to that risk use case. Security is also scalable, where users can have granular access control on the portfolio, firm, or process flow level. LEX was also built to be able to process large numbers of documents in batches. It has processed around 150,000 PDF and Word documents in nightly incremental batch processing. It is also able to process around 10,000 files per hour and can also process zip files. Finally, aside from the batch processing of documents, LEX also has the sandbox interface. The sandbox allows the user to access the LEX application in real time by giving the user the ability to create and test different types of lexicon rules and upload a document to analyze results. Since LEX was put into production in 2018, the number of users and use cases have grown not only in New York, but also across the system, such as in Chicago, Philly, and San Francisco. LEX is being used by a variety of supervision users from across every portfolio. Most recently, due to the COVID-19 epidemic, subject matter experts created a lexicon to identify pandemic risk and capital impact due to pandemic. User feedback has been very positive. They report that their analysis has gone from hours to minutes, and that LEX is especially useful to analyze large documents containing hundreds of pages. LEX has become the de facto NLP platform within supervision and continues to expand. We hope that with the continued use of LEX, analysts will become more efficient and effective in their day-to-day jobs. In the next section, I will be talking about how LEX works under the hood. LEX's unique algorithm combines rules with machine learning to identify accurate risk sentences. It takes in a lexicon of terminology and a word embedding model. The lexicon is a rule set and is built by subject matter experts. It contains a set of trigger terms and attributes. A trigger word is usually considered a specific risk term or phrase, for example, concentrations or contingency funding. The attributes are usually generic terms that modify these risk terms, such as significant or material. The word vector model is an open source model built by Google called Word2Vec. The Word2Vec algorithm uses a neural network model to learn word associations from a large corpus of text. In this case, Google has used its news sources. You can think of Word2Vec as a machine-learned thesaurus. A sentence is a match if an attribute and trigger both appear in the sentence, and they also have a linguistic link between them, as in they are referring to one another. Let's dive a little deeper into the matching algorithm. A sentence has to pass 2 levels of matching in order to be considered a match. First, the terms have to appear in the sentence. In the example lexicon, the highlighted rule 18 is expanded into 3 rules. The sentence is flagged if it has words that match either concentrations and high, or concentrations and significant, or concentrations and material. A single row within the lexicon is processed as a rule within the NLP engine. Each rule is labeled with 1 or more categories. In this use case, these are risk types such as credit risk or market risk. However, you can imagine that the lexicon can contain any language of interest and can be separated into different categories. The matching algorithm in LEX uses both exact and similar matching. Exact matches are considered keywords and are hyphenated. Highly specific risk terminology such as CCAR or MRA. These are acronyms which can be considered as keyword matches. Similar matches are the generic words that can be found within the word vector model, such as increased, high, significant, or material. Since the words concentrations and significant are not hyphenated, they are looked up in the word vector model. For the sentence example that was highlighted, it can be seen that the word concentrations matched exposure with a threshold of 0.47. This means that the cosine similarity between the vector representing the word concentrations and the vector between the word exposures is 0.47. The word significant matched the word significant with a threshold of 1.0 because it's the same word. We decided to set the threshold to 0.45 because we found that it was matching words that were not just exact matches or synonyms, but those that had semantic similarity. This level produced minimal noise, but also gave interesting matches that analysts would not have discovered themselves. The second level match is the linguistic match. After the terms in the lexicon are matched either with keyword or word-to-vec matching, a check is done to see if the words have a linguistic link between them. This means that there is a dependency between the words when the sentence is parsed. This check is done to make sure that the significant was about the exposure and not about something else. The LEX NLP engine was built in Python and Java. We have mostly used open source libraries such as Spatie and Textasy for the linguistic analysis, GenSim and word2vec for semantic analysis, and Apache Tika for PDF highlighting. For future work, we are enhancing LEX's lexicon development and machine-learned word embedding model. We are creating a tool that will give suggestions to users of relevant words and phrases based on understanding existing risk language. We are also building a word embedding model with our own internal documents so that we can find similar words to the highly specific risk terms within the documents. This could potentially eliminate the keyword matches. These enhancements will make the creation of the lexicon faster and more accurate. It will also improve semantic matching of words, which will improve accuracy of results while minimizing false positives. Thank you for your time, and I'd be happy to take any questions you may have.